Hello, this is Nick Chancellor, and I'll be talking to you today about some experiments I've done on some D-Wave chips with Viv Kendon. These are reverse annealing experiments, and I'll explain some of what we're doing, and it gives us some interesting insight onto how the noise on D-Wave devices works and what effects it have. Our work is in this archive paper here that you can see on the first slide. And let me get right to it. To start off, let's just remind ourselves how regular forward quantum annealing works. The way this works is you have fluctuations, which are driven by a transverse field, effectively bit flipping, and then you have a problem, Hamiltonian, which is, in this case, written in as an Ising Hamiltonian. How to map actual problems to this. There'll be other talks discussing this. I won't really talk about it here. But the point is, when these are both turned on, you have complicated quantum effects. When only one of these is turned on, it's effectively classical, actually, for either one. So, and regular forward quantum annealing is you just start with only this one on, with only the transverse field on, and go to only the problem on. So, in contrast, reverse annealing is you start with the problem turned on, the problem Hamiltonian, and a guess state. And so we define this annealing parameter we call S, which determines this ratio of A and B. And basically what we're looking for here is we effectively turn B down and turn A up. So turn the problem down, turn the fluctuations up, wait for a while, and then go back, read out. And this allows you to start from an informed guess rather than zero. Thermal dissipation seeks low energy states while you're doing this. That will be important later on. But yeah, that's the idea. So why would people want to do this? Well, it turns out, as I kind of hinted at before, starting from zero isn't maybe the best. What you'd prefer to do is to start from a good guess. There's actually all kinds of very nice algorithms that people have done with these and promising proof of concept results. That's not what this talk is about, but I did want to just throw a slide up with some examples. There's getting to be so many examples that they don't fit on a slide. I very much like that, but yeah, plenty of information there on the different things people have done with this and lots of very nice work. So what we're concerned with here isn't how reverse annealing can be used in computation, it's how it actually works. So what we're going to look at is how to build experiments to test it. So the idea is, if we're thinking of a concept of a local search, what we want is we want some feature that would trap forward annealing, otherwise you could just do that instead. A starting state and a true minimum nearby that you could get trapped, that you can find by starting near it, whereas you'd usually get trapped. So I'm not going to go through the details of how this Hamiltonian is actually engineered. This is the spin Hamiltonian we use. The details can be found in our archive paper. We didn't just come out this out of the blue. It is inspired by some previous work by others, which again, you can find details of in our archive paper. So if you saw my AQC 2018 talk, this will look very familiar. I actually showed preliminary results on the same experiments during that talk. And the preliminary results there were pretty much that reverse annealing works as it's supposed to. It does indeed perform local search. And you can see here in this sort of meta plot I'm pointing to now, a plot from a previous talk, you have this nice peak in the middle of the true minimum. This is S prime. This is how far back you search. I'm now using S star just because that seems like a better convention. You go here. If you search too broadly, it's like a forward anneal and you get stuck in the false minimum. Of course, if you don't search enough, you just stay here. Every once in a while, you find some other solution. You can find this talk on YouTube. So what's new since then? I'm not just going to tell you about old results since 2018. I'm going to tell you about what's going on since then. Well, for one, we got more data points, but it really just confirms the gist of what I said in my 2018 talk. Reverse annealing does what it says on the tin. It does what it's supposed to do. However, a nice thing here is when we did these experiments, we had access to both higher and lower noise D-Wave QPUs. This was when the lower noise models were coming in. So this allows a detailed understanding of the effects of the noise. So here I've just given some examples. You can see lots more data points. In this case, the left column is the lower noise, the right column is the higher noise. Again, I have this sort of S star, and the difference between the top and bottom is just how big this barrier here is. And if it's not there at all, it goes, in both cases, very easily all to the true minimum. But when it's there, you actually get less going in the true minimum on the lower noise QPU. And we'll talk about that some more. But before we get to that, how do you compare results from different QPUs? These are from different physical systems. So what I plotted before was against this S star parameter, but that S star is not necessarily meaningful without thinking about sort of physically how the device works. So what we actually want is this ratio of these A and B parameters, and I call that gamma. And that's a way to fairly compare between two different devices. Because both A and B have dimensions of energy, gamma is a dimensionless ratio. And you can see here sort of what some of the schedules look like. And yeah, so if we plot in this way, we can see two effects, two key features. The first feature we notice is that for the lower noise QPU, that's the one on the left, you actually have to go to a much higher gamma star. Notice the different scales here on these x-axes to get to the same success probability, the same probability to be in the true minimum. In other words, it takes, or the false minimum. In other words, it takes more fluctuations to get anywhere than on the lower noise QPU. And the second one is what I mentioned on the previous slide, that peak probability in the true minimum is higher for the low noise, is lower for the low noise QPU for the same T, same tau, same wait time. So these plots are for different wait times. And so let's first focus on the difference that turns out to be kind of boring, which is that you need a higher gamma on the less noisy QPU. And this basically comes down to the fact that the dissipation is actually what's driving the reverse annealing. And so if you have less noise, that's less coupling to the bath, less opportunities to dissipate. You can see if you have a longer runtime, what happens is, so longer hold times, longer tau, you basically don't need to have as high of a gamma. This makes sense because you have longer time to tunnel, you need weaker tunneling. This is probability to be in the true solution, by the way. Interestingly, and I'll come back to this later, the height of these peaks doesn't really change, at least not in a very consistent way as this tau is changed, and that will be important later. A quick aside for what's going on here, before I get into the more exciting effect, there isn't direct tunneling going on between the local minimum and the true minimum and the false minimum. What's actually going on here is something else. It's going to be some more complicated process where you're jumping through multiple levels. How do I know this? Well, I can do numerical diagonalization and find that the gap is very, very small. And so the inverse gap, the time scale that I would need to run things for to actually see direct tunneling is just much, much longer than the longest time scale I used in my experiment. In fact, our numerics actually ran out of steam before we found how small the gap actually was. But at some point, it's no longer worth doing the numerics, because finding out that the gap's even smaller won't affect our results of our experiments. So most importantly, this is not MRT. This is not macroscopic resonant tunneling. That's been done. They're very interesting experiments. You can find them here, but that's not what we're doing. So now for the more exciting difference. The noisier QPU has a higher peak in the probability of the true solution. And so that's exciting because it shows that something's going on that's making the lower noise QPU able to find the true solution easier. Here I've just swept a parameter I call JT, which controls the height of the barrier between the true minimum and the false minimum. And you see, as this barrier gets higher, the difference between these two gets more pronounced. So this is basically indicating longer range tunneling. The next obvious question is, okay, I'm claiming this is longer range tunneling. For that to be true, right now I've just shown that the probability is not going into the true minimum. Is it actually going to the false minimum? The answer is yes. You can look at that pretty simply by just saying, okay, what's the maximum value of this plateau before you get to a big enough gamma star that everything just goes to 1. And you see that, again, for the lower noise QPU, at these low levels, you tend to branch more into the false minimum, again, indicating longer range tunneling on the lower noise device. So let's actually model this. Let's go one step further and actually try to get an understanding of how these are working. So what we can do is we can just make a simple model of how the probability to be in the false minimum depends on time. Let's just model it as exponential decay and have this R false, and basically say, all right, we immediately branch between the true and false minimum from the starting state. That's a good approximation because I can see here that it doesn't depend much on the hold time, at least at these low values of gamma. So almost instantaneous, or branching there, that happens very fast. And then it doesn't really depend on tau up at these higher values. And we can apply this model and fit it, and we see, again, the same thing. That what really is going on is that there's a branching ratio which favors a further away state for the lower noise QPU. Lower noise means longer range tunneling. So it confirms our model, and there's a longer range search. So this is very exciting, and it suggests a reason for why the lower noise QPUs have been observed to perform better on spin glasses. That was observed in these very nice experiments, but there wasn't much of an explanation given. Now we're showing, okay, you're having more coherence, you're able to tunnel further, that's what's going on. So very interesting result for understanding the mechanism. Very quickly, what's next? Well, what we've done, these effects here, could be very useful in trying to figure out open system models here. This isn't really directly my field, but it's likely to be fruitful if someone does it. We have this sort of interesting experimental effect we've uncovered. And to this end, the data have been made publicly available, the data from these experiments. It has a DOI you can use there, or if you don't want to copy down the DOI, it's also linked from my webpage. So, takeaway messages from this real quick. First off, from the beginning, reverse annealing has proven to be a powerful technique for hybrid algorithms. And so if you haven't yet, it's worth trying. This isn't really part of the actual results in the talk, but I'm just going to put it out there. Lower noise leads to longer range search, and this explains why this lower noise QPU performs better. Further noise reduction is likely to be a promising route. However, one interesting thing here is these devices that do, when you do reverse annealing on them, you're actually fundamentally relying on dissipation to do your search for you. So there has to be some sweet spot, because if you made the noise go to 0, you wouldn't have the effects that are actually making your reverse annealing work. An interesting open question that I'll leave you with is, does the same kind of sweet spot exist for forward annealing? In other words, is it best to eliminate all the noise, or are you better off actually keeping some of this noise that dissipates out energy because it's useful? I don't have an answer to that, but it is an interesting thought to conclude the talk on. Thanks for coming to my talk. My understanding is there will be a question and answer session where I can answer any questions people have. And thank you very much.